Okay, well that's just coming up there is today's tutorial. Okay, I just want to say a couple of little things about it in a moment when we get the photocopy of the practice. You will see from the practical that's going around that I thought it was such a good idea that I'm actually asking you to implement the sieve of Eratosthenes. And I've given you a brief non-functional description of it, what it is. So you're going to have to do a bit of research perhaps to find out how it works so that you can implement it. And I think I've asked for a program, a complete program that will implement the sieve of Eratosthenes for numbers up to about 20,000. So you have to think about a way of doing that. You don't have that much memory on those development systems, so every byte is important. You have to be careful with every byte. What else? If you look on the internet, you'll find loads of information about the sieve of Eratosthenes. I was only looking for a short time. I didn't find an assembly language version of it. And so even if there was one, I wouldn't recommend that you take it and copy it. The thing is that the internet is very useful for finding out things about overall how the thing works. Find out how it works and then implement it. Okay, you can implement something that's pretty fast. Okay, it's very like this, okay? So I'm not going to go on as I normally do. I'm not going to go and try and solve this tutorial today. Instead, we might revisit it after you've done the sieve of Eratosthenes practically, because the approaches and the techniques that you'll use, a big hint here, will be very similar. Is that okay? Good. Okay, I'm glad of that. What I will do is I'm going to have a look at the practical that I asked you to do this week. And I'm just going to make some general remarks about it, because many of you did very well. I think for the first time I've seen 11s and 12s out of 10, lots of 8s and 9s and so on, and a few 5s and 6s. But that's to be expected. But a very good performance. But let me just give you a couple of pointers to the way that I think that the thing should have been approached. You had a 5x4 matrix, right? And you had a 4x2 matrix. And you had to produce a 5x2 result. And the key to this thing really is thinking very carefully about how you will represent the matrices in memory. You don't have to represent the matrices the same way. So even though you have two matrices with whose elements are words, you don't have to use the same representation scheme for both. Okay? You can use whatever representation scheme you prefer. So obviously the third matrix, the result matrix, is a matrix of numbers, so of course it has to be a bit different anyway, somewhat different. So it seems to me that if you look at the thing as 5 rows, okay, 5 rows, okay, and then we have sorry, There's 4 elements on each. Okay. They're the elements, okay, those little boxes on the lines. I'll explain the lines in a moment. And then you'll have 4 by 2. So this is the way that you might think about it. You've got 5 rows, and here you've got 4. You've got 5 rows of 4 elements, and you have 4 rows of 2. So what I've been trying to do is draw the lines like this, because what you're going to be doing, right, is you're going to produce one of the results at the end. Okay? You're going to have to add the products of the corresponding elements in the row going across here and the column going here. Okay? So this element here would be the sum of this multiplied by that, this multiplied by that, this multiplied by this, and this multiplied by that. Okay, that sum will have to go in there. Now, as Mr. Nolan, I think it was, pointed out, it is theoretically possible, so therefore it will happen, that when you sum these 4 partial products, you get a result that overflows along it, because you multiply words by words to produce long words, and I think I agree that it's possible that there might be overflow. I'm not quite certain. I still want to think a little bit about it. But I think it's, on the face of it, certainly it's possible. So there's an inherent problem with this, the formulation of this problem, of this practical. Nevertheless, let's just go ahead for the sake of the practice. Okay, so what I'd be saying is that you're going to be multiplying this by this, or sorry, these pieces by these pieces to form a result. These pieces by these pieces to form another result, and so on. So you'd be going across there, and you'd be going down this way. Okay? Going down here all the time, and then when you've all that done, you move on to the second column. Now, what's that got to do with anything? Well, you know about that. I mean, you know how matrices are multiplied, although my grip of it is a bit vague at the moment. The thing is that these things are going to be stored in memory. And if you're going to multiply, say, this by this, and then you're going to add in this by this, you must be able to reference these things in memory wherever they are. And the obvious thing, and the wrong thing, would be to say, well, this is element number 1, 1, this is element number 1, 2, this is element number 1, 3, and so on. And to use these indices as inputs to what you might call a storage mapping function. Which would take, let's say, the address of the base of the array, and the indices, and the size of each element, and the way everything is laid out, and would produce an address. So if you said, I want to get to element number 2, 2 of matrix A, you can find the address of this location. So you could do that. That would be a general solution, right? And if your program requires you to be able to hop around from one part of the matrix to another, say to pick out an element for some reason, then that approach, having the storage mapping function, would be fine. However, we're not in that situation here because we know that the order in which we access elements in the array is very predetermined. Okay, we know, for example, that if we're at this point here, the very first element, the next element we're going to want to look at is this one. Right? Why not arrange in memory for this element to be very close to the first element? Okay, so that means why not store the second element in a row beside the first element in the row? Okay, we've got a choice, you see. We could imagine storing the second element in the column beside the first element in the column. But in this case, I'm suggesting that for ease of programming, we're going to store the second element of the row beside the first one. So we're going to store the first matrix row by row. Okay, that means that if we start with, if we calculate where this is, where the first element is, we can get to the next element very easily because it's right beside it. In fact, it's 2 bytes away from it, the size of the element in memory. Okay, so that makes it easy for us to walk along the first matrix row-wise. if we look at the second matrix, we don't want to go row-wise, we want to go column-wise. So why don't we store this column by column? So that's what these lines mean. I think this might be called row major, and this is column major. Anyway, here we're storing row by row by row by row by row, and here we're storing column by column. So I'm making up the data structure that I'm using to represent these matrices to suit myself, to suit the operations that are being performed. And that's the key to this, because it makes life so much easier. Let me point out something else to you. At the end of, let's say we multiply the first two elements, the second two elements, the third two elements, the fourth two elements, and we're using an address register to point to each, okay? And maybe a third address register to point over here. But thinking of these two address registers, at the end of the row here, the address register will actually be pointing to the first element of the next row if we arrange for this element to be next to the last element here. If it's row-wise, then our address register here will always automatically be pointing to the next row. And we only have to change that when we come to the end of the matrix, having finished processing this. Okay? So each time around, then you have a loop which will allow us to calculate these partial products, and then we'll have another loop that will allow the thing to walk down the matrix here, and then we'll have yet another loop to allow us to go from one column to the next column here. So I envisage loops nested 3D in order to solve this problem. Okay, so that's the way that I would have gone about that. Right? So will we just go ahead and put in a few sample values here? So let's say A dc.w. Okay, so we're going to define this. And we're going to define it row-wise. So let's give these things values for the sake of appearance. So we might give this one here the value 1, 2, 3, 4, 5, 6, 7, 8. Just values, right? Nothing special about them, but you'll be able to see how they get defined in memory. Okay, so we're going to store this row-wise. So we've just defined dcw 1, 2, 3, 4. Now, so I can do this. 1, 2, 3, 4. So I'm defining the row there. Okay, now define constant words, and there'll be a word containing 1 followed by a word containing 2 followed by a word containing 3. So we'll have the row across there. And we'll just do the rest of them. 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, and 17, 18, 19, 20. Okay, now for this one here, let's use, well, let's start at, say, 30. 30, 31, 32, 33, 34, 35, 36, 37. Now we want to store these column-wise. So actually what I want to define constants would be 30 followed by 32, followed by 34, followed by 36. Okay. So we'll have B, dc.w, 30, 32, 34, 36, and then dc.w, that's column-wise, 31, 33, 35, 37. Okay, and then we need space for the result. C, we're going to have, what did I say here? A 5 by 2 matrix, that's 10 long words. And we just say ds.l 10, space for the 10 long words. We could imagine setting this thing up with, say, A0 pointing to A, A1 pointing to B, and A2 pointing to C. And we could generate our unit step. Maybe I'll just do part of the inner loop. It's a very iterative process, and I'm sure I'm going to get this wrong, and I'm going to have to correct it. Okay, I imagine that's the way that you might have gone about it too. This is very tricky stuff. It's very intricate stuff, and despite the fact that I have done it before, I'm very likely to make mistakes. So bear with me, please, and don't be put off too much if you yourself are making lots of mistakes. Gosh, this is completely the wrong way going about it. Okay, so what I'm going to do is I'm going to do the inner loop that's going across, let's say, the top row there, and going across the first column. So I'm assuming that A0 is pointing to A, that A1 points to B, and that A2 points to C. I'm just assuming that for the moment. I might change my mind about that, but that's where I'm starting. So, and I know that what's going to happen, I'm going to have to load. So temporarily, I'm going to use A0, A1, A2. Let's say I'm going to use A4 to point to A0. So A4 is my working copy of A0, and A5 is the working copy of A1 that I'll be using, and A6 is the working copy of A2. I may not need A6. Okay, so what I'm going to do is I'm going to load A5 with A1. So now I have A5 is pointing to the first column in B, and I'll assume that, so this is going to take a little bit of work. A0 is pointing to A4, so the A4 pointing to A, and let's say, for the sake of it, A2 to A6. So, I'm going to clear D7. Okay, sometimes you begin to start worrying about speed of instructions, and I know some of you were doing that in the practical. Move quickly is as fast as it gets. You can use clear.l, but I think it's just as fast. Right? You can check. Okay, so what we'll have is a little loop counter 4 minus 1. Okay, I'm going to use B6 here as a loop counter, the number of elements in a row. And I'm using -1 for a reason you'll see in a moment. Okay. So it's a multiply, well, so we move what's at A4 and post increment it into, we'll say, D5. Okay, we'll multiply that by what's in pointed to by A5.
Why is it sign words?
Oh, there's sign words. Okay, well, multiply sign. Thanks. Okay, multiply them together. Okay, and then add D5 into D7, and then we can subtract. No, I'll just leave that at 4, not 4 minus 1. I'm getting ahead of myself. Subtract quick, long, value 1 from D6, and branch, if not 0, to, we call it I loop, the inner loop, the innermost loop, which will be to here. Okay, I'm thinking of another instruction which I must introduce you to. In a little while. Okay? So this little bit of code here then, being done 4 times, we're initializing an accumulator effectively to add the partial products together. Okay? So what we have to do now around that, just outside that, is to try to get it so that A5. Oh yeah, once we've done that, let's just finish the job here. We'll store the result, D7, we store the result out on the result matrix, which is at A6, post increment. Now let's just think about what we've got here. What we've got is we have a register pointing to the start of the second row in matrix A, and we have a register pointing to the second column in matrix B. Well, we want to get that back. We want to get the pointer to the second column back to the first column. So we will, we can say move long A1 into A5. So reset pointer to B, to the first column of B. Then we must be doing this 1, 2, 3, 4, 5 times. So we need to put all that in a loop as well. And if we have it in a loop, and let's say we're using D4, that's our next free data register, D4 as our loop counter, we could be subtracting. This is where it gets a bit non-linear. D4 to the next row. And we could say branches, we haven't finished that to, well, it will be the middle loop, the M loop. So M loop will be back up here somewhere. Excuse me now for a second. M loop will be, I would say, possibly here. Okay. And so we will have to, before we get into that loop, we will have to initialize, actually I'll just put this in yellow here because I'm sticking this in, and there'll be more put in. I'm going to put 5 into D4, that's my counter that I'm using now. Okay, so M loop is here. Okay, so what we have now is a bit of code that will do the following. It will calculate the sum of those 4 partial products for each row and that column there. So at the end of all that, what we have to do is reset the pointer that we're using to point to matrix A back up to the start. Okay, and we have to set the pointer that we're using here to point to the next column. In fact, it's already pointing to the next column, as you would, because we have defined this column-wise. And we walk down this column here, reach the end, we're effectively pointing to the next free space here for the next column. So we don't have to do anything with A6. We have to reset A4 to the start and A5 will take care of itself. Okay, so we can simply say we want to move along A0 back into A4, so back to the start of A. We want to subtract 1 from our counter of the number of columns in the result, which will be D3. So we have to initialize D3 up there. Branch of not equal to, we call it the outer loop. The outer loop. Oh. Okay, that should be yellow as well. So the yellow stuff here is just stuff that I put in after writing it the first time. So that label is also new. Okay, now that's not quite right because it isn't resetting A0, so that's okay. arguably okay in it. So you see I have a triple loop. One for calculating, I think they might be called inner products, I'm not sure, I don't remember that stuff anymore. One for walking down the rows of the first matrix, and then the other loop for walking across the columns of the result. So intricate code. Yes, sir.
Do you not need to reset A5?
Do I not need to reset A5? Well, A5 gets reset up there. This is the way the code looks, right? It gets reset there. So I think that was the last thing I was just thinking of whether I was going to do that. I think it's done there. So it drops out at the end here. It always resets A5 to go. Okay. Yeah, you're right. Yeah. So there is a mistake in it. Thank you very much. There is a mistake in it. It'll be tricky enough to fix. I won't be able to fix that now, but there is a bug in it. The bug is that the second time around, when I'm trying to generate the second column of results, I need to make A5 not point to the first column, but rather the second. And my code is always resetting to the first column. So I can't just think about that right now. That's definitely something that I would have to fix as I was looking at. Was there another question? Yes, sir.
You need to initialize D3 as well from all.
Do I need to initialize? Yeah, I need to initialize D3 to 2. So I'll do that here. Thank you very much. That was just an omission. Just to go back to this point here, my recollection of it is that the ordering of these is important. And these can be brought inside the outer loop and the middle loop to give us the effect that we want. But I just can't think it through while I'm talking to you guys. Okay, but that's the approach that I would certainly have used. Now, you might say, apart from the fact that there's clearly a big and obvious bug in it, once that bug is taken out of it, you might say, well, gee, this is special pleading because you're taking a problem and you're just making up a data structure to suit yourself. Well, the answer is, yeah, I am. That's one of the things that I can do at assembly language level. In fact, you can do it at any level, but it's easier at assembly language level because you can see what's going on. And it turns out to be very important. Not so much in these situations, but as I was trying to explain to somebody the other day, we're assuming wrongly, rightly in the case of the development systems, but wrongly in general, that these programs that we're writing are running, accessing real physical memory. In other words, you make a reference to a memory location and the piece of hardware immediately gives you back whatever is there, or stores whatever you want to be there. So we're assuming real physical memory. Now that is not the case in most computers. Okay, it is the case in small embedded computer systems, but it would not be the case on PCs and Macs, right? And so that means that access to memory locations is normally very cheap, as it happens, but occasionally it's very, very, very expensive when you get what's called a page fault. Now, the way that you lay out a matrix, especially if it's a large matrix, in memory, whether it's row-wise or column-wise or something else, can have a huge effect on the paging behavior of your program. Absolutely gigantic. The cost, by the way, of a page fault, access to memory in a modern computer is certainly of the order of 100 nanoseconds. Right? That's 10 to the minus 7 or 10 to the minus 8, even maybe 10 nanosecond, 10 to the minus 8 seconds. Access to it, to a memory location, if there's a page fault, is of the order of 10 milliseconds. Okay? So there's a huge discrepancy and a huge cost, therefore, if you get a page fault. The way you lay out matrices and the way you access the elements in the matrices has a very big effect on page fault. So very often, for big scientific problems where you're manipulating matrices, you will worry very much about exactly how a matrix is laid out in memory to avoid page faulting. So it's something that isn't going to go away. And you'll find out more about that when you look at operating systems and so forth. Okay, so that's that. Now, next week's practical, you've already seen a flavour of. So now I want to start a new topic because, like I said last week, I'm afraid we're getting bogged down in the minutiae of programming. It's very interesting, a bit of fun, but I want to move on to something new. And what I want to move on to is input and output. So I want to introduce in the remaining few minutes, I want to introduce the idea of I/O, input and output. And the first question is, what is it? Okay, what you've been doing and what you've been programming in and all that kind of stuff is a world which comprises the processor, 68000, with its registers and all that kind of stuff. Okay, and memory. Now, never mind that there are different kinds of memory. That's the situation. Okay, and you also are somewhat aware of the bus, especially if you're looking at instruction timings, because you know access to memory is extensive in terms of time. It takes about a half a microsecond to get a word from memory. So that's the world you're programming in. Okay. Registers, the program counter, the condition code register, the instruction set with the addressing modes, memory. So where does the real world come into this? Well, let's draw a boundary line here and say that outside of this boundary line here is the outside world. Okay? So the question is, how does the program that lives in this world that you write for that kind of world where you're dealing with numbers and memory locations and bytes and execution timing and stuff, how does that actually connect with the outside world? And the answer is pretty neat in the case of the 68000 and its predecessors. And let me draw a slightly different way. So we're wondering, how do you get to something out here? Okay? My cat. Okay. Let me ask you to look at this a slightly different way. Slightly different way. Okay? So we have the processor over here. And you can think of, this is all a big metaphor or analogy. You can think of yourself standing there, okay? You're the processor, okay? And you execute the instructions and you fetch. It's a natural enough thing to identify with, especially if you're a geek, okay? Over here is memory. And these are the locations. Okay, they're the locations, and they're numbered 0, 1, 2, 3, and so on. Okay, and in between them, and you've seen this picture or something very like it before, there's the bus, right? So that's what's going on. Now, to look at it a bit more closely, what's going to happen? Suppose you say, okay, I want to read what's at this memory location here. Let's say this is memory location 1, 2. I want to read whatever is there, and I want to put it into data register 2. And the instruction goes to location 12, reads the piece of information across the bus and puts it into D2. So you're familiar enough with that as you use a move instruction. Okay, thinking sort of physically here for a moment, what's behind this ability to access stuff at location 12? Well, there's a piece of RAM, there's a piece of random access memory in a chip, and it's got a controller around it, and there's a whole lot of stuff, wires and all that kind of stuff, which is, as it were, behind these locations. So when you make a reference in your program across the bus to a memory location, a physical operation takes place which activates the RAM device, picks up whatever electrons and so on are there, interprets their significance, and returns a value. Okay, so that's what happens. So, in a sense, accessing a memory location is where, sort of metaphysically, if I may misuse the word, your program, which is a kind of an active thing, actually physically accesses a piece of the world. So, what I'm suggesting then is, rather than have your instruction just access a memory location which gets to RAM, why not have it access a location, say up here, that actually is a gateway into the outside world, where the cat is. Right? Okay, in other words, you might think of a location as a kind of a window into the outside world. You say, what the hell is that? Well, of course you wouldn't access the cat or something like that directly. You would access a peripheral device like a keyboard or a switch or the cat flap on the door or something like that, right? you wouldn't be accessing the outside world directly, you'd be accessing a peripheral, or an interface. Okay, so joking aside or flippancy aside for a moment, what I'm suggesting is that memory locations, or let's say generally locations, instead of always physically connecting you with a piece of RAM or ROM, that they physically connect your instruction with an interface which in turn connects you to the outside world. So a switch, for example, here's an electronic picture of a switch. It's very simple to understand. This thing here at an angle is a wiper, and when you press the switch or activate the switch, the wiper closes, allowing you continuity from the top line there through the closed wiper to the bottom line. So you close the switch, you establish continuity there. If you have a logic 1 up there and a logic 0 down here, which is easy enough to implement, when you close the switch, this 0 will be changed to a 1. Okay? If you could arrange for this kind of functionality to be connected through the interface into a memory location, you could read that switch's value as a 0 or a 1 as the value of a bit at that location. Now, the physical means of doing that is the business of physical interface design. Okay, and that's beyond the scope of the course. We can certainly talk about simple ones, and we will. But it's not so much the physical side of it, because that is taken as a given in this course. It's what you do with that information. So suppose this switch indeed is the switch on a cat flap, which indicates the cat wants to get in the door, like he's butting his head against the door. What do you do with it? What's the significance of the fact that the switch has changed? Well, it's a piece of information. The cat is at the door. But it's also a piece of information about when this event in the real world is taking place. So the way that you program, the way that you write programs to deal with the outside world obviously has 2 dimensions to it. One of them is the data in question, and the other is the timeliness of the data. And we'll see that there are ways of working out when it's appropriate to use the information, when it's appropriate to rely on the information, and when it's appropriate to send information out. So input-output programming is about, first of all, finding out something about these interfaces, and then secondly, rendezvousing or synchronizing with the information, either information coming in or the right time to send information out. That's what I/O programming is about. Anybody got any ideas about how you might wait, so to speak, for the cat to press the cat door with a program? Okay, let's imagine, right? Let's imagine that this is the cat door switch. The cat presses it, it goes from 0 to 1 when the cat presses the switch. How would you write a program that, so to speak, knew when the switch was pressed? You'd have a loop, yeah. You'd write a piece of code that would go in the loop. It would keep checking that bit, you would say bit test on this location here, and wait for that bit to go from 0 to 1. Any problems with that? Sorry, excuse me for a sec. Yes?
When it runs a loop, it will branch off and leave the part of the code you're waiting, so you know where to go back in.
Yeah, we'll come back to that one. That's a bit more advanced now, right? Anybody else? You can't do anything else. That's a very good point. It's pretty stupid because it just sits there. And that looping, waiting for something to happen in the outside world, is called polling. P-O-L-L-I-N-G. Like you're asking for somebody's vote. You're saying, what is your intention? What's your stance? So it's a direct analogy with asking somebody what their preference is. So it's called polling. And that loop is called a polling loop. And it is a tremendous waste of time, because the computer can probably ask, 100 million times a second, or certainly 10 million times a second. And the cat isn't going to be doing it all that often. Right? So you can see there's a bit of a mismatch there. Nevertheless, it's very, very, very rugged. It's very easy to do. And if the computer is cheap, it doesn't really matter. Yes, sir?
Does the 68000 have threads?
Does the 68000 have threads?
Yeah.
No processor has threads by itself. But if you were to ask me, can you implement threads on a 68000? Very much so, yes. And we probably will towards the end of this course. I hope we will implement very simple threads. Okay. So you're getting way ahead, and you're even more ahead than Brady. So maybe you both know each other. I don't know. That's cool. Okay, so you can imagine then that you could poll for something to happen. right? And we'll do a lot of that. Is there any other way you could arrange things? I don't know, what's your name? Andrew. I know Andrew is sort of heading in a particular direction here. Is there any other way that you could imagine finding out that something had happened in the outside world? In this scenario, right, you have the cat pressing a switch which puts a 0 to a 1 or a 1 to 0 or something here. You can certainly code looking for the information. Could you imagine any other way, perhaps more efficient? Okay? Now I know this is a reach, but let me ask you anyway. You could check every so often. So you could say, well, I'm not going to check every tenth of a microsecond. I'll check every millisecond or every 10 milliseconds because it's only a cache, right? Yes, you could do that. Any other way of doing it? Could you imagine any other way of doing it? Okay, well, let me suggest a general way. If you think about coding, you write a program, and it's the responsibility of the program, and therefore the processor, which runs the program, it's its responsibility to find out what's going on here. Okay? It has to keep asking, because this guy isn't going to tell it. You could imagine in that world a different situation where the interface device had a way of telling the processor. The processor could be off doing something else, calculating the civil veracity or whatever it is. It could be doing something else. Wouldn't it be nice if the interface could somehow signal the processor